now we have this second talk of today by Neumayer from UT Austin, and she's going to talk about a strong form of the quantitative Wulff inequality. Thank you.
Thanks very much, and thanks very much to the organizers for this very nice conference and this opportunity to speak. I'm enjoying the conference and the chance to experience Rio. So the talk will be organized as follows. First, I want to introduce a couple previous stability results for the isoparametric inequality, then introduce the anisotropic case, and then we'll talk about some strong form stability results for the Wulff inequality. So let's recall the isoparametric inequality, which says that the perimeter of a set E is greater than or equal to the perimeter of a ball of the same volume. And we get equality if and only if our set is a translation of the ball. So today we're interested in the question of stability, saying if our set E almost attains equality in the isoparametric inequality, then how much does this set E look like the ball? So to talk about this, let's make precise what we mean by almost attaining equality and what we mean by looking like the ball. So first we'll introduce the deficit, denoted by delta of E, for how close we are to equality in the inequality. So it's just the perimeter of E minus the perimeter of the ball. It's how much we lost. And then one notion of looking like the ball that we'll introduce is the asymmetry, denoted by A of E. And let's understand this definition by picture. We take our set E, we translate it to where it makes sense to compare to the ball, and we take the measure of the symmetric difference. So there's a celebrated stability result for the asymmetry that was first proved by Fusco, Maggi, and Pertelli that says the asymmetry is controlled by the square root of the deficit. And this exponent of decay is sharp. But I actually want to focus on a much earlier stability result that holds only for a smaller class of sets, but within that class of sets is actually a stronger result. So this is a result of Fugletti. Let me first define a nearly spherical set. This is a set that has the same volume as the ball, the same barycenter, and is a small normal perturbation. So given the ball, we go out in the x direction, continue in the normal direction, a distance specified by some function f, some function u, we've called it, and in this way we parameterize the boundary of our set. So for this class of sets, Fugletti showed that the h1 norm of this parameterizing function u is controlled by the square root of the deficit. So within these small normal perturbations, the Fugletti result says the h1 norm of u is controlled by the square root of the deficit, while the Fusco-Maggi-Pertelli result is just the L1 norm. So this is a stronger result within this class of sets. So let me say two words about Fugletti's proof. He gave a Taylor expansion of the deficit and got this term here on the right, and then expanded this function u in the basis of spherical harmonics, that is, eigenfunctions of the Laplacian on the sphere. And then used a gap in the spectrum of the Laplacian to show that this term on the right controls the h1 norm squared of the function u. So then Fusco and Yulin came along, and they said, given the Fugletti result, can we expect to control a stronger h1 type quantity for general sets of finite perimeter, not just ones that are small normal perturbations? And the answer is yes. So they defined an h1 type quantity that's suitable for all sets of finite perimeter. Take my word for it that it's the right definition. More or less, we're taking an L2 norm. In an L2 sense, we're measuring how much a normal vector of E aligns with the corresponding normal vector of the ball. And this gives us a measure of the oscillation. And for sets that are small normal perturbations, it's equivalent to the h1 norm. And what they showed is that this h1 type quantity is also controlled by the square root of the deficit. So precisely what they did is they extended this Fugletti result to all sets of finite perimeter. Okay, so now I want to shift gears a little bit and introduce the anisotropic perimeter. So the main idea is the following. For the standard perimeter, in some sense, the ball is our reference set. And now we're going to fix another bounded convex set and replace the ball and use this set as our reference set. So let's take this set, we'll call it the Wulff shape. And we define the support function f of nu as the sup of x dot nu for all x in this Wulff shape. So it's easy to show that the supremum is attained by the x for which nu is normal to a touching hyperplane decay. So let's see here. With this nu, it's normal to this hyperplane, which is a touching hyperplane decay at this blue point x. So f of nu is given by x dot nu for this x. This gives us a geometric interpretation of f of nu, it's the distance from the origin to the touching hyperplane decay with normal nu. So, okay, given this, let's define the anisotropic perimeter, which is denoted by p sub k of E, and we get it by integrating over the boundary of E, f of nu E. Nu E is the outer unit normal of our set. So take a minute and note, if we choose our Wulff-shaped K to be the ball, then f of nu is just the Euclidean norm, and this K perimeter reduces exactly to our standard notion of perimeter. For the anisotropic perimeter, we get the analog of the isoparametric inequality. This is the Wulff inequality. It says that the K perimeter of a set E is greater than or equal to the K perimeter of K among sets of the same volume. And again, we get equality if and only if our set is a translation of the Wulff shape. Stability in this case was shown by Figali, Maggi, and Bertelli in their proof of the stability result for the isoparametric inequality. It extended to this case. Okay, so they showed that, again, the asymmetry is controlled by the square root of the deficit. So, given what we've talked about so far in this talk, there are a couple natural questions. Can we obtain an analog of the Fugolette result in the case of the anisotropic perimeter, in the case of the Wulff inequality? That's to say, if we have a set that's a small normal perturbation of our Wulff shape, then should the H1 norm of that parameterizing function be controlled by the deficit? And, okay, if so, then what about the Fusco and Yulin result? Can we define the appropriate notion of an H1 type quantity, even for sets that are not normal perturbations, and can that quantity be controlled by the deficit of this function? So in that direction, let's define a nearly K set to be, again, okay, a set E is nearly K if it has the same volume as the Wulff shape, the same barycenter, and it's a small normal perturbation. So here we have to assume a bit of regularity on K, but so again, we go out in the X direction, continue in the normal direction, a distance specified by a function U, and in this way, parameterize the boundary of our set. So for these sets, we can show, okay, assuming that our Wulff shape is C2 and uniformly convex, then we can show that the H1 norm of this parameterizing function is controlled by the square root of the deficit. So a word on the proof, we start in the same way as Fugolette did. We do a Taylor expansion of the deficit, and we get this. This is the same term that Fugolette got. If our Wulff shape is the ball, this grad squared f term is just the identity, and the mean curvature of the ball is just n minus 1. So it's the term we saw before. So now we want to expand our function u in the basis, now not spherical harmonics, because the natural basis to consider is the basis of eigenfunctions of the operator that arises integrating by parts in this first term above. So we do that. The problem is we don't have explicit information about the spectrum. In the Fugolette case, well, we know everything we want to know about spherical harmonics. We know the eigenfunctions, we know the eigenvalues. Here we don't expect to have explicit information. We're talking about a general class of elliptic operators. But what ends up saving the day is the fact that this Figali-Maggi-Bertelli stability result shows us that there is a gap in the spectrum. So even though we can't expect to quantify it, we know there's a gap, and in this way, we're able to bound this quantity on the right-hand side from below by the H1 norm squared. So this is exactly the Fugolette result in the case of the anisotropic perimeter. So how about the Fusco and Yulin result? How about when we're not just a small normal perturbation? So after defining the appropriate anisotropic notion of this H1 quantity, we can show that if we have a uniformly convex and C2 Wulff shape, that this H1 type quantity is controlled, again, by the square root of the deficit, this optimal rate of decay. Great. So a word about the proof. We use a tool called the selection principle. This allows us to reduce to the case of almost minimizers of the anisotropic perimeter. If you're familiar, what I mean is lambda are not minimizers. Then we use the regularity theory for these almost minimizers, plus the fact that we're L1 close to the Wulff shape. And this allows us to reduce to small normal perturbations of the Wulff shape. Okay, well, we already discussed this case. This is where we already proved the Fugolette type theorem. So this is great, but we also would like to say something even without assumptions on our Wulff shape. Before we said for this theorem that we want a Wulff shape that's C2 and uniformly convex. But so in the case where we just take any Wulff shape, we can still say something. We show that, okay, this H1 type quantity is controlled by the deficit not to the power 1/2, which we do expect to be optimal, but to the power 1/4 over 1/4 plus 1/4n. However, we definitely expect that the power 1/2 should be true in this setting. And more evidence in that direction is the fact that, okay, we saw that for the case of uniformly convex C2 Wulff shapes, we can show this optimal power of decay, 1/2. Now, if we go to the very other end of the spectrum, we let K be a convex polygon in R2. So this is definitely not uniformly convex and definitely not C2. Here we can also show this H1 quantity is controlled by the square root of the deficit, this optimal decay rate. So finally, a quick word on this proof. So again, we use the same reduction technique by Ciccolesi and Leonardi, the selection principle. And it takes us to the case of almost minimizers of this anisotropic perimeter. And the thing is, when we haven't made any assumptions on K, we only get very weak regularity properties. If you're familiar by this, I mean uniform density estimates. So we don't have as much to work with, and this is why we can't get the power 1/2. But in the case of the 2D polygon, there's a result by Fagali and Maggi that says that if you're an almost minimizer of this anisotropic perimeter, then your set E is also a convex polygon whose sides align with those of K. And so from this point, we've reduced to this. It becomes an explicit computation using the area formula. Okay, so obrigada.